So in the last class we discussed about the theory of one port negative resistance oscillator. So in the theory of one port negative resistance oscillator states that to make a negative resistance device such as gun diode or tunnel diode or any similar negative resistance diode, we have to satisfy the two conditions. One condition is the RL should be greater than 0, Rin should be less than 0. So this is the one of the condition. We can, here it is written for the load resistance RL plus R out equals 0. And another one condition to be satisfied is XL plus X out equals 0 or RL plus R in equals 0. Similarly, XL plus X in equals 0. So this condition have to be satisfied to make the negative resistance device to oscillate. Here we know that so one condition is RL plus R in equals 0, and another one condition is XL plus X in equals 0. We know that this RL is greater than 0 because it is a load resistor. Therefore, the load will be a positive 1. RL is greater than 0. Since it is positive, this load implies it dissipates the energy. In order to satisfy this condition, then R in should be equals minus RL, that is negative. Since RL is positive, therefore R in should be negative in order to satisfy this condition, and R in becomes less than 0, is a negative, and the negative resistance implies it is a energy source, whereas the positive resistance RL implies it is a energy dissipating element. Similarly, here this condition should be satisfied to control the frequency of oscillation. So this condition is to control the frequency of oscillation. So these are the two conditions needed to be satisfied to oscillate the negative resistance device. Now we see the procedure to design the negative resistance one port oscillator. So this design problem is design a one port oscillator using negative resistance diode. The diode is having gamma in equals 1.25 angle 40 degree. The characteristics impedance Z0 equals 50 ohm at its desired operating point. for f equals 6 gigahertz. Design a load matching network for a 50 ohm load impedance. So this is the design problem that we have to design. So the given diode which has the gamma in equals 1.25. Now you can see that the gamma in value is more than 1. For the positive resistance device case or in general, the gamma in value will be varying from 0 to 1. But here you can see that the gamma is more than 1. So this is the one indication by which you can understand that this is a negative resistance type device. So most of the time the gamma in is more than 1, which indicates that the device is negative resistance property, can oscillate. Then the device is this one, it's the diode, and we have to make the biasing to operate the diode in a negative resistance region. Just like in a gun diode, the characteristics will be voltage versus current. As we increase the voltage, the current also increasing. It is a linear region. There, it up to a particular point, we are calling this point as the threshold voltage Vt. If we increase the voltage further beyond this voltage Vt, then the current will be decreasing as the voltage is increasing. This will happens up to a certain voltage level, that is we are calling valley voltage. If we increase still the voltage further, then it follows again in a positive region type, and this region we are calling as negative resistance region. This is minus R, negative resistance region. Then we have to bias the diode in such a way that it is operating in negative resistance region. Then we can choose any voltage or current in this region. Therefore, let us say I have taken this point as my biasing point, then the corresponding bias voltage will be Vb. Similarly, the corresponding current to this Vb, the bias voltage is Ib. This is a DC current, this is a DC voltage. This is called Q point. So now this diode, how to make or provide this DC voltage or to bias the device is this diode, a negative resistance diode, and the top of the diode we have to provide the voltage, that is the DC, through a RF coil. So we have a resistance and then we have a RF coil, and top of it we apply the bias voltage V bias. This is RF choke, and in the load normally the oscillations will be connected to the subsequent RF subsystem, that is represented by load. Load normally 50 ohm. This inductor, this is the R bias resistor, and the current through this resistor is IB, bias current. So this IB current can be obtained by having a suitable bias resistance and also apply the bias voltage. And this bias voltage is slightly greater than this voltage because some amount of voltage will be dropping across the R bias. And the role of the coil inductor is RF coil is, this RF coil only allow the DC current to flow through the diode to ensure the Q point. Whereas this coil will prevent the flow of RF current through the bias network. Therefore, this coil will do the isolation work to prevent the flow of RF current and to allow only the DC current. Then as per the requirements, we have to transform this 50 ohm source into the required gamma L value. For that, we are introducing one network is called the impedance transformation network. So this network is the impedance transformation network. This is the load, this is the diode, this one is the diode. So this is the way of making the bias to operate in the required Q point level. You can choose anywhere over the negative resistance region. Not only here, you can choose this point or this point, anyone you can choose. So this is about the biasing of the negative resistance diode to make it oscillate. So the design steps are, first we have to compute the Zin, input impedance of the diode, corresponds to the given gamma in. The gamma in equals 1.25 angle 40 degree. By using the Smith chart or any analytical method, we can find the Zin, input impedance of the diode. By the analytical method, we can use this formula. Zin equals Z0 1 plus gamma in by 1 minus gamma in. Now you write the gamma in terms of rectangular form. So you transform 1.25 angle 40 degree in rectangular form. Now that value will be 0.958 plus J 0.8. Now we add with 1 the numerator, then the Zin will be equals, Z0 is 50 ohm system, therefore 50 ohm, 1 plus 0.958, it will be 1.958 plus J 0.8 divided by 1 minus this value will be 0.042 minus J 0.8, which yields the value is minus, after the inside the square bracket, the value will be minus 0.86 plus J 2.496. Then you multiple with 50. It gives the value minus 43 plus J 124.8. This value is closer to this. Because of some truncation, we have got this value minus 43 plus J 124.8. Anyway, this will become close to this value. You can compute this way, or you can use the Smith chart to compute the Z in. For that, you have to locate this point gamma in on the Smith chart. The Smith chart, the maximum gamma value is 1. Here this value is more than 1, that is 1.25. So we have to plot this point. So either you can use the analytical method or the graphical method. So by using the Smith chart, you can compute the set in value, which gives you the normalized value actually. Then afterwards you have to multiply with 50, then you will be getting the exact Z in value. So here we have done this computation using the analytical method by using the formula Z0 1 plus gamma in by 1 minus gamma in, which gives us minus 44 plus J 123 ohm. So next thing is, we have to find the load impedance. Here the load impedance ZL should be minus Z in, so negative of this. If you read from the Smith chart, you remember you won't get negative minus 44, you will be getting plus. For the real part, you have to make it negative, because we did a transformation here, that's why we have to make the real part into negative, and the imaginary part, that you keep it as it is. Whatever value that you are reading from the Smith chart, you can keep that value as the imaginary part. For the real part, you have to change the sign, okay, it will be negative, or it will be better to use the analytical method using the formula to compute the Z. Next you compute the load impedance, and load impedance equals minus Z in, so negative of this value. So negative of the value will be plus 44 minus J 123 ohm. This is our ZL required. This is the load impedance required. But the actual load impedance is 50 ohm. Here you can see that this is the actual load. Now we have to transform this load into the required ZL value, this value. For that, we have to design a impedance transferring network. So this network that we have to design. Let us see how to design this network. So this is the one that we need it. First you compute the normalized load value, lowercase zl, which is equals actual load value zl divided by z naught. That is the characteristics impedance. It is 50 ohm. So this is a 50 ohm. The characteristics is 50 ohm. Therefore, use the 50 ohm. You do the normalization on ZL. So this normalized value will be equals 0.88 minus J 2.46. Now you mark this normalized load on the Smith chart. 0.88 minus J 2.46. Now you mark this on Smith chart. So in the Smith chart, the real part is 0.88. So this is 0.8. This one is 0.9. So it will be very close to this one, 0.88. You follow this circle. And the imaginary part is minus J 2.46. So the 2.46 is, this is 2, this is 3, this one is 2.46. Now you move from this circle and also moving through this circle, these two will be intersecting here. So this is the point ZL, normalized load impedance ZL. You mark this point on the Smith chart. Once you mark the point on the Smith chart, now you draw a straight line from this point to the center of the Smith chart and also extend the line in the opposite direction, and also you extend the line in opposite direction. This way also you extend it. So this is the ZL. Now you have to draw a circle with a radius of the center of the Smith chart to this point ZL. Now you have to draw a circle. It is the best practice to draw a circle. You do draw it. Or you measure the length of this line from the middle of the Smith chart to this point. You measure the length using the linear scale. Then you mark the same distance in this line from the middle of the Smith chart to this. You mark it. It is same as drawing a circle. Okay, that's why I am telling the another way. It is best to draw a circle. If it is not possible you to draw a circle, then you measure the length of the line from the middle of the chart to this point. Now you mark the same distance in the opposite axis. That point is YL, normalized load admittance. So this is ZL, is opposite will be normalized load admittance point. Okay. And the next step is, now you move from the center of the Smith chart, that is, this is the center of Smith chart. You move on a unit circle. Okay. Now you move on the unit circle from the center of the Smith chart. This is a unit circle you move in. You can stop here. Where you have to stop is arbitrary one. Okay, you no need to stop here always. You can stop either here also, or you can stop over here, or you can stop over here, anywhere you can stop it. So for one particular solution we stopped here and you stop over here. Now you read the reactance. So the reactance will be corresponds to this point. This is the unit circle where we have stopped. This is the point where we have stopped. Now you read the reactance. This is the reactance. So the reactance is located at 0.308 lambda. This point is 0.308. This one 308 lambda. Now you measure the open circuited stub from the extreme left end of the semi-chart from here. From here you measure the distance on wavelength towards generator scale. Now you measure it. You all the way come through around the semi-chart and you stop here. It is 0. This is 0.308 lambda. Therefore, the length of the stub, that is the open circuited stub, is 0.308 lambda. Now we have computed the length of the stub. This one we have computed. The length of the stub is 0.308 lambda. Next we have to compute this length of the series transmission line. For that, now you draw a line through this point. This is the point we have stopped. Draw a straight line passing through this point. The straight line is same as the load line. Therefore, we needed to draw another one line because this point is marked on the load line only. Therefore, this is the straight line. Okay. Now, from this line, you measure the distance. So, from this line, you measure the distance, you move around the semi-chart until you reach this point, the YL, the extension of the YL. And the extension of the YL equals 0.052. This one. This point is 0.052. Then from here 0.25 to up to this will be 0.25. Okay. Then this distance can be the difference between this 0.303. This point is 0.5. This point is 0 and this is 0.25. Again, when we complete one full circle, we have traveled 0.5 lambda. That is 0.5 is equivalent to 0 lambda. Okay. So this point is 0.303 minus 0.5. You will be getting 0.197 lambda. This is the distance between this point, that is 0.5 minus 0.303. So the distance between this and this one is the difference between these 2 points, that is 0.197. Then you have to add the distance to be traveled extra to reach this point. This point is located at 0.052. Therefore, you have to add this 0.052. This point you have to add with this. So, the length of the line will be 0.249 lambda. So, this is the length of the line. L equals 0.249 lambda. So, this is 0.249, which is approximately 0.25, the same as this. A small error will be coming when we use the semi chart. That depends on our the tool accuracy, that is our pencil sharpness, and how we are weaving. Our eyesight also playing a major role to get the exact reading from the semi chart. Therefore, a small difference will be coming always, that is permitted. You no need to worry about it. So, 0.249, which is approximately equal to 0.25, which is same as the length of the line. Now, we have designed this transformation network by using Smith chart. So, this one is we have used Smith chart. This is the load, actual load. This is the negative resistance device. The biasing is not shown in this diagram. Actually, the bias will be will have a current limiting resistor and followed by one inductor which is connects over there. Okay. So, this completes the entire design. So, this is the procedure to design the transformation network to transform the 50 ohm actual load into the required gamma L or corresponds to ZL using the Smith chart. So, this completes the design. So, the next class we discuss about the transistor oscillator and its design techniques.